Okay, the 2022 applied maths paper has just been released, a bit later than the other ones. So just give initial reaction to what came up here. Well, the motion question is your standard. They've kind of brought back the standard motion question of trains meeting. So train 40 minutes from rest, station A to station B. Distance between stations. Yes, brakes applied. Yeah, so it's not two trains meeting, but speed time graph. So very traditional motion graph. Time taken for the first 16 kilometers, that should be fine. Deceleration of the train, yeah, should be reasonably okay. This one, again, quite a traditional one. Ball thrown up and another ball thrown up later. So it's got, basically this one will have the equations with t minus 8 in it. From the same point, same initial speed, so you take the same u for both of them. Find where the ball is after 5 seconds. So the first one and the total distance it's travelled, so that's fairly okay, that's grand. Prove that when E and F collide, they'll be both travelling with a speed half gt. Okay, that's an interesting one, but it looks reasonably okay. Ship travelling 22 kilometers a direction, both sends out to intercept it, so you get your standard triangle there. Find the direction the boat should steer. Okay, so that sounds similar to, I think, question 2 years ago. Time to the nearest minute it takes to intercept the ship, that should be grand. And the distance between the boat and the ship 10 minutes before they meet, so getting the relative velocity there and using the time there, and that seems okay. Relative, or the river crossing one, is a bit unusual in that, okay, they've kept numbers out of it, which makes it look kind of interesting. So this is the first time I think I've seen where they've kept it generic, and you're getting the general formula for a river crossing. So she can swim U in still water, so that's your relative velocity. So velocity of the woman relative to the river is U. She cover a distance of D against the current in time T. That's a little bit ambiguous there, but okay. Okay, and the same distance with the current in time T2. Okay. Okay, so T2 is going to be a lot less. Okay, right. Current flows parallel straight back. Yeah, so V. Prove that V, the speed of the river, is equal to the distance D, T1 minus T2. Yeah, so T1 is going to be the larger one. So the difference between the times over the product of the times halved. Okay, that's an interesting one. As first time I've seen a general one for the river crossing. Okay, so V is less than U, so they're telling you that the river is slower than the woman, which is unusual. Normally it's the other way around. So the woman could go straight across, in other words. Okay, find in terms of T1 and T2 time taken across the river by the shortest path. So shortest path in that case would be straight across, vertically across. She can go vertically across because her speed U is going to be bigger than the river. Okay, so straight across, which should simplify that one. Okay, 3. Okay, the projectiles one. Projected out to sea. Interesting. First time I've seen that being projected out to sea. Oh yeah, from point on a cliff. Okay, so you're starting with SY being plus 60. Oh, well, okay, on a cliff. To hit a target 60 kilometers horizontally. Okay, so actually no, it's SX is 60. And 60 meters vertically below P. Okay. So you're given SY and SX. Okay, fine. Okay, you're given U. Find 2 possible values of alpha. Okay, that should be okay. And the times of flight should be all right. Particle projected up a plane. So, okay, so they're given a general one again here now for the inclined slope. So that's an interesting one. Plane is inclined at 30 degrees horizontal. Greatest range. Greatest range. Okay, you're getting the general expression for the maximum range. That is a very complicated derivation normally. Now, it's probably simplified because you're given the angle of inclination there. But yeah, so that's quite a derivation, I'd say. But yeah, so that might have tricked people a little bit, but the first bit should be fine. Connected particles. Okay, so block, lightest vegetable string. Okay, so two particles here. That's unusual. Okay, D is connected by another light inexpensible string, so two strings there. Coefficient of friction. Okay, so you have friction on the table. Separate diagrams, forces acting on each block. Okay, that should be all right. Find the and it should kind of set people up for the whole question. Acceleration of C and tension in each string. Yeah, so you've got two strings there. Should be okay, but unusual. It's haven't seen it before, I think. Okay, pulley atop a wedge. Okay, yeah, so it's a wedge. Can it move? Yeah, it can move, yeah. That's an interesting one, yeah, because you've got a moving wedge with a pulley system, so it's a combination question. Okay, makes an angle of that. 3, system release from rest. Yeah, so you've got resolving all those forces in and out of the wedge and parallel to the wedge. Okay, acceleration of the wedge. Okay, yeah, an unusual one, probably a little bit more tricky than normal there on the connected particles. Okay, looks straightforward, these two bashing into each other. Coefficient of restitution, speed of each sphere after collision, should be straightforward. Magnitude of impulse, okay, impulse is change in momentum, but that's come up 2 years ago, I think. Loss of kinetic energy due to collision is this. Find the value of K. Okay, not often that they bring in kinetic energy. That's relatively new, but hopefully should be straightforward. Oh, another kind of generalish one. Collides obliquely with a smooth sphere. An angle, so initially an angle alpha, and then an angle beta. Oh, with that line. Interesting. It's turned through an angle of beta. Yeah, that's an unusual way of putting it. Normally they give you the absolute angle, but shouldn't be a problem in that they are alternative angles. So basically the angle before is alpha and the angle after is alpha plus beta. Okay, so probably have to use a few trig identities to resolve the alpha plus beta, but should be okay. Show the tan beta expression for that. Okay, that should be all right. All right, and let's see what came up for the actually that one is very like the physics question that came up. Moves in a vertical circle, greatest and least tensions. That is fascinating. Okay, that simple harmonic motion question is very similar to what happened in the physics paper. I wonder, do applied maths and physics coordinate with each other, because this is very similar. It looks like they didn't in this case. Because period of the motion, yeah, you were asked that in the physics one as well this year. Okay, show that it satisfies that. Well, that should be okay. So differentiate that once, you get a cos, differentiate it again, you get minus sine. So it's should be fairly straightforward. Very unusual to see a second differential, but that should be okay. This one, so the tension is 3T down here and it's 1T up there. But yeah, very similar to the physics one. Okay, let's have a look at the calculus one. Okay, differential equation, this. Okay, that should be fine, integrating that with those two bounds. Minimum value of V, okay. Right, that should be, okay, so minimum value of V, setting that equals 0. All right, Find the distance travelled by the particle since it before it attains maximum speed. Okay. There's always an exponential then, so pretty used to this. Proportion the amount of substance remained. And yeah, radioactive decay, bit like the physics again. Okay, find the value of K. That should be okay. Yeah. Overall, I mean, what would be my reaction overall to it? I think it's probably, there's a few unusual ones, I'd say. Very interesting in that that's very like the physics question that came up. The collision question, probably part A, fine. The oblique one, I'd say was tricky. Probably tricked people a little bit. Connected particles, probably a bit more difficult than normal, I would say. No standard pulley question with a movable pulley in the middle kind of thing. Projectiles, I'd say this is fine, but that one would have been tricky. The inclined plane, given a general equation for that. The again, part A should have been all right here, relative velocity, but this one, the general equation might have been tricky enough for people for a river crossing. Never seen that before. That would have been standard, and that would have been standard. So the motion question was okay. Some of them, I would say, probably in general terms, a reasonably tricky paper, I would say. More tricky and a bit more. But this is the thing about applied maths, it tends to be quite innovative, different every year, and they're always rethinking it. And it always stretches people, which is partly why it's such a great subject, and it really gets the best out of students. But this one, I'd say, would have stretched people, but it doesn't matter. I think everybody, it tends to, because everything runs through the bell curve, it tends to average out. But I think this one would have been a bit more of a tricky paper than the last couple of years.